And one big idea is that an electric circuit is a closed loop. So this is what a setup would look like in a classroom. We've got a switch, a light bulb, and a battery, which is our source of energy. And if we were to open the switch here, so if I were to open this up, then we would have a gap, and then the light bulb would not light up. So again, you must have a closed loop. I like to think about the word circle and circuit having the same root and meaning a closed, well, circle is actually the locus of points equidistant from a center point, but also thinking of a circle as a closed loop. Okay, let's think then about what voltage is and what resistance is. So remember that volts are joules per coulomb, and so that's energy per unit charge. So what we think about if we look at a simple circuit like the one above, I'm using gravitational potential energy as my analogy here. The battery acts like a pump that lifts the charges up and gives them energy. Now in this analogy, it's gravitational potential energy, but it's not really gravitational potential energy. It's electrical potential energy that they get. But they've got this energy and they go and they go and then they get to a resistor. And when they get to the resistor, they spend that energy by doing something. Now, in the case of this picture where we've got a flywheel, they do work, and that's where the energy goes. In the case of this light bulb, the energy is dissipated, because light and heat are really just energy dissipation, meaning that the energy goes from the system of the light bulb out to the environment of the air. Let's see, other reminders. Voltage, potential difference, and electromotive force are all the same thing, depending on who you're talking to. If you are talking to an electrician, so if somebody's rewiring your house, they're going to call it voltage. If you talk to a physicist, which I don't think I spelled that right, they're going to say potential difference. And if you talk to an engineer, they're going to say electromotive force. But they all mean the same thing. Again, it's electric potential energy. And it's energy that is carried by the charges that are flowing around the circuit. We talked about electric current. Electric current is rate of charge flow, so it's charge per unit time. So back up to this analogy, I would think about the height that the charges are lifted would be the stored potential energy, but then the amount of charge, so like you could have a trickle of charge, or you could have like a deluge of charge, like a whole bunch of charge. The amount of charge per unit time, that's your current. And then I think we kind of ended up with this. We talked about how electrons are moving in the conductor. However, in the United States, we use something, thanks to our buddy Benjamin Franklin, we use something called conventional current. So in the US, we model positive charge flow. In the rest of the world, they model it a little more scientifically correctly because it is the negative or electrons that actually do the flowing. Okay, let me pause there. And so I'm going to resume this. So the question was, what's different about a capacitor? So a capacitor is two charged plates. So first of all, to charge up the capacitor, I would need to hook it up to a battery or something. And the battery would act like a pump. And if the capacitor starts with an equal number, I'm just going to do this in a different color, If the capacitor starts with an equal number of positive and negative charges, what the battery does is it pumps electrons from the positive to the negative. So it's going to take these electrons and make them go over here. It's pumping them like a pump pumps water. So when that process is done, when that process is done, oh dang, there we go. When that process is done, we end up with a plate with a net positive charge and a plate with a net negative charge. Now I'm really previewing what's coming up, but it takes time for this, for the voltage to be put across the capacitor. It takes time for the charges to be moved from one plate to the other, and it happens in a logarithmic fashion that looks like that. Okay, now let's say though for a moment that I disconnect the battery. So now I just have this charged up capacitor, and actually while I was doing this I should have had an open switch here. Okay, and now let's say that I close the switch. Boop. When I close the switch, what's going to happen? What do those charges want to do? They want to equalize, right? They want to have they don't want to have a net positive and a net negative. They want to be in equilibrium. So the negatives are the ones that move. So the negatives are going to move until, again, we've got equilibrium. And while they're moving, while these negative charges are moving, that's current. And you're going to have current flowing through this resistor. So if this resistor were a light bulb, you would have the light bulb glowing for a while, but after the capacitor becomes in equilibrium again, then the light bulb stops glowing. Oops, it really stopped glowing now. This is different than a battery. A battery has chemicals where as long as they keep reacting, the current will keep flowing. So again, the capacitor, it kind of goes, it usually goes pretty fast. It usually discharges pretty fast. The bigger the resistor, the slower it will discharge, but it's not going to last forever. A battery, again, can last for hours and hours or days and days because it's a slow-going chemical reaction that's producing that charge flow. And that was something in chemistry, and this is a little, I'm not going to do a great job here, but basically if you put a metal and an acid, it makes electrons move around. So that's that is the very, very brief explanation of a battery. So the circuits that I'm showing you here, like this circuit that I'm showing you, this is not what's in a guitar amplifier. The integrated circuit in a guitar amplifier, or if it's not integrated, the soldered circuit in a guitar amplifier is super complicated. And you have to go to electrical and computer engineering school to really understand the whole thing. It is, there's going to be capacitors, there's going to be logic gates that turn different parts of the circuit on and off. There's going to be other kinds of like power conditioners that keep the voltage steady so that things don't fry. In a solid state circuit, everything's on an integrated chip, but in the older things there are tubes, vacuum tubes that help condition the power, like they look like light bulbs. Anyway, all of this to say there's a lot more to it. And I can't, well, I'm not really prepared to explain it all because I can't pull it out of my brain right now. I don't even know if it's in there. I don't know if you guys know, like kind of at the edge of your knowledge, there's things that you understand, but you can't explain them to other people very well. That's where I am with the guitar amplifier situation. Anyway, sorry. But this is really just an introduction to all that stuff. And if you did open up, I mean, I'm sure you've seen the inside of any kind of device. You know, like if you've looked on the inside of a computer, you know, I keep showing you like a light bulb with a battery. There's a few more loops than that in here. You know what I'm saying? Um, yeah, you know what I'm saying. So we're just kind of warming up to it. Other questions?